students. In this video, we are going to derive the expression for the loss of head due to sudden enlargement. So before we start the derivation, let's do a quick recap on what happens in the control volume. First of all, when a fluid is flowing through a pipe, this section 1 pipe, and it comes to this point where there is a sudden enlargement or abrupt change in dimension, there will be a loss of energy due to turbulent eddies, because the fluid cannot trace the boundary exactly due to the sudden change of the dimension, so leaving a gap at this point. So, and this point results to loss of head due to the sudden enlargement. So we have a drag force here, which is opposite the fluid movement as P2A1 in this pipe flow. So in order to derive the expression for head loss due to sudden enlargement, there are 4 equations that we're going to consider. And the first one is Bernoulli's equation. Second one is the force acting on the fluid. The third one is momentum of fluid. Then continuity equation. First of all, let's apply Bernoulli's equation at section 1 and 2. So we have that P1 rho G, P1 over rho G plus V1 square over 2G plus Z1 is equals to P2 over rho G plus V1 square over 2G plus Z2 plus HE. So since we are dealing with a horizontal pipe, that means the elevation at first section and second section are the same. So that will cancel out. Then you make HE, because that's the area of interest, subject of formula. So they have change in pressure over rho G plus the change in kinetic energy. So we now have our equation 1, and we are trying to express this in terms of velocity, not pressure. So thereby we are going to apply another formula in order to eliminate this pressure head. So the next equation here we're going to apply is the force acting on the fluid. You know, for every flowing fluid, there is a force that is pushing it to move at a certain rate. So, and the force is equal to pressure times area. So for the first section, we have that P1 times A1. Then for the point of sudden enlargement, you have P prime, which is experimentally proved to be the same as P1 times A2 minus A1 minus the drag force, which is in the second section, which is P2A2. So here we replace the P prime with P1, so that we now expand the equation in this form. You have P1A1 plus P1A2 minus P1A1 minus P2A2. So these two will minus, it will go. Then you have P1A2 minus P2A2, which will now result to this equation. Simplifying it further, we now have this change in pressure times A2. So this is the second equation derived from force acting on the fluid. Then the third equation here is the momentum of fluid per seconds at section 1. So we're going to consider the momentum at section 1 and section 2. So, you know, when the force is applied on a fluid, there are a certain amount of fluid that will flowing within a specific period of time. So we have change in mass with respect to increase in force or decrease in force. Therefore, we have mass here in terms of mass flow rate times velocity. So, and mass flow rate is the same as density times volume flow rate. So we have density times volume flow rate multiplied by velocity. Then when you reduce this further, you know that volume flow rate is the same thing as length times area over time, and length over time is velocity. So at the end of the day, you now have rho A1, this one will now turn to V1 times this V1. You have this equation. So at the end of the day, you have rho A1 V1 squared. So you repeat the same process in section 2, so that you arrive at this equation, rho A2 V2 squared. So the change in velocity, the change in momentum is equal to momentum in the second section minus momentum in first section. And our equation for the force acting on the fluid, in our second equation, which is the force acting on the fluid, we have change in pressure times area, and we know that area 2. So, and we know that the force acting on the fluid is equal to change in momentum. Therefore, we need to remove this A1 so that we solve in terms of A2. So that's why we applied continuity equation, and continuity equation is given as A1 V1 is equal to A2 V2. Making A1 subject the formula, you have A2 V2 over V1. So change in momentum per seconds will now give you rho A2 V2 square minus rho times A1 will now be replaced by this equation. You have this times V1 squared. So when V1 cancel V1 squared, you have only V1. So at the end of the day, you now arrive at this equation, which is rho A2 V2 squared minus rho A2 V1. Having these two equations have common terms, which is rho A2, you bring it outside the bracket, then put V2 squared minus V1 V2 in the bracket. So now equating the force acting on the fluid with the momentum of the fluid per seconds, we have that change in pressure times area 2 is equals to rho A2 bracket V2 squared minus V1 V2. So that area 2 will cancel out. You cancel this. So you're now left with rho A2. You now make the pressure head subject. So you have rho change in pressure all over rho is equals to V2 squared minus V1 V2 squared. So in order to make it look like the first equation, which is pressure head all over rho g, we have to divide through by g on both sides. So when you divide by acceleration due to gravity, you have that change in rho all over rho g will be equals to V2 squared minus V1 squared over g. So substituting the value in equation 1, substituting the value of change in pressure over rho g in equation 1, you now have that the head loss due to sudden enlargement will be equal to V2 squared minus V1 squared over g plus V1 squared minus V2 squared. So this is a common fraction that you now solve based on simple mathematics. So you find the LCM, which is 2g. When g divide 2g, you have to multiply by the numerators, you have this value. Then 2g divide this, you have 1, multiply by the numerators, you have this. You have 2v squared minus v2 squared, so that you have v2 squared plus v1 squared minus 2v1 v2. So this is an algebraic expression that can be factorized into this form, making it to be v1 minus v2 all in bracket square over 2g. So this is the best way to drive the sudden enlargement expression, and it will help you to know which technique to apply in exams, so that you don't get confused along the line. So you need to have it in back of your mind that that rho 1